Hello students, this is Mr. Maat with another physics lesson. In this lesson I will start with showing you the outcomes of two homework questions. I will show you how to deal with them and how actually to solve them and get to the correct answer. Well, after that I will have a bit more theory. I will recap amplitude and wavelength, and will always also focus on frequency, pitch and the cycle time. Make sure you finish all the assignments for next lesson. Okay, let's start with the first question. That was question 7. Aisha and Salma are doing an experiment to measure the speed of sound. They stand 150 meters apart. Aisha starts the stopwatch when she sees Salma make a sound, and she stops it when she hears the sound herself. She measures the time as 0.44 seconds. Calculate the speed of sound in air. Okay, so the first thing that you do is you write down all the things that are given. We're going to solve this question, of course, in ROPEX style. So the first step is write down all the things that are given and make sure that everything is in standard units. You see, the thing that I'm going to calculate is the speed of sound. Well, the standard formula to calculate the speed of something is, of course, taking the distance and divided by the time. So I fill it in over here. I get 150 divided by 0.44 and I get 340 meters per second. Make sure that you write it in standard form. So 3.4 times 10 to the power of 2 meters per second. So that is the speed of sound in air. Well, the next question starts like this. The speed of sound is approximately 340 meters per second. What is the speed of sound in kilometers per hour? Well, we did this with the chapter of speeding up. So if you don't know how to deal with this, I recommend you to view those movies as well. So what we want to know is the speed of sound in kilometers per hour, and we know the speed of sound in meters per second. Well, how to convert this is just by using a factor of 3.6. So if you want to go from meters per second to kilometers per hour, you just multiply the value by 3.6. So that's what I did over here, and I get a value of 1.2 times 10 to the power of 3 kilometers per hour. Okay, now question B. A student hears 2 echoes when she claps her hands. One echo is 0.5 seconds after the clap and one is 1.0 seconds after the clap. How far apart are the buildings? So I made a bit of a drawing over here, and you see there's a person standing, well, not in the middle, but from a distance S number 1 to the left building and distance S number 2 to the right building. Well, let's first start by writing down all the things that are given. Well, the first thing that is given is, of course, the speed of sound, 340 meters per second. Meters per second is my standard unit, so that's perfect. Well, I know the time that it took for the sound wave to travel to the ears of this person, 0.5 and 1.0 seconds. Make sure that you understand that this is actually the time that it took to travel twice the distance, because she claps. The sound wave travels to the building, bounces back and travels the same distance again. So the time over here is actually the time to travel twice the distance. Okay, the plan is like this. We need to use 2 formulas. We want to calculate S number 1 and S number 2. Well, we do that with the standard formula for velocity, and we rewrite it a bit so the distance equals the velocity multiplied by the time. Well, the total distance is, of course, distance number 1 plus distance number 2, that's over here. So let's calculate this. So I calculated distance number 1 by taking the speed of sound and multiplied by the time. I get 170 meters. The distance of number 2 is 340 meters. But now take a good look. I already mentioned that this is actually the time to travel twice the distance. So there are 2 ways to solve this. First of all, you can just divide this already by 2. But if you do it like this, of course you need to divide those values by 2 as well, because it's an echo. So I divide 170 by 2 and I get 85 meters and 170 meters. So if I want to know what is the distance between those 2 buildings, I just add those 2 together and I get 2.6 times 10 to the power of 2 meters. Well, this was a question that something similar you can expect in the test. So make sure that you understand how this works. Always with an echo, it travels twice the distance. That's the thing that you should focus on. Okay, let's start with the theory. This was a theory of last lesson. I told you that this was the equilibrium position, the neutral position of those molecules. And if those molecules start vibrating, we call this the maximum amplitude, and the maximum amplitude is over there as well. And the amplitude was the maximum displacement with respect to the equilibrium position. And this was the equilibrium position. So that is actually just the distance that you can measure. So the thing that you should remember is, the greater the amplitude, the louder the sound. Smaller amplitude, you get a quiet sound, less decibel. Okay, we also talked about the wavelength, and the wavelength was actually the distance between two consecutive points. So you can take the two tops or the two values over here. That doesn't matter, you always get the same outcome. It's the length of one wave. Well, now let's talk about two other concepts, and that are cycle time and period time. They're actually exactly the same. So sometimes I will talk about cycle time, sometimes about period time, exactly the same. Okay, the period time is now, it looks like it's the wavelength, but take a good look. I placed over here now the time on the horizontal axis. In the previous one, it was the distance. Now we're talking about the time. So the time that it took from one top to another top is actually the cycle time or the period time. So the time required for one complete wave. Some students find it difficult to figure out what actually is a wave. Well, take a good look over here. The wave, of course, starts over here. This is half a wave, and this is again half a wave. So that means that this, in total, is one complete wave. So you need to have one top and one valley. You can also start over here, then this is, of course, half a wave, and this is again half a wave. So the time required for one complete wave, we call that the cycle time. Well, the cycle time is something that we can study. And the cycle time has its abbreviation, and it's a capital T, the same as temperature. But you can recognize if it's temperature or cycle time by just taking a look at the standard unit. And the standard unit is time, and so for time is of course seconds, but the waves are very small, so sometimes we talk about milliseconds. Well, there's of course a relationship between the time that it took for one wave and the total amount of waves per second. Well, the total amount of waves per second, or the number of oscillations per second, so an oscillation is just a wave, so the number of waves per second, we call that the frequency. So in a graph like this, you can't tell me anything about the frequency, because you need to know where is 1 second. So if I place 1 second in this graph, now you can tell me something about the frequency. Now it's just counting how many waves you see in 1 second. So let's start over here at 0. So I call this half a wave, a complete wave, and again half a wave. So the frequency over here is 1.5 Hertz. So the frequency is a quantity that we can study, and the abbreviation for it is a lowercase f. The unit for it is Hertz, a capital H and a lowercase z. Okay, so the frequency is the number of oscillations per second. So you always need to look in the graph, well, for 1 second. And it doesn't matter if you start at 0 and then end up at 1. You can also start over here at 9 and end up at 10. Well, in that case, this is half a wave, this is a quarter of a wave, so it's 0.75 Hertz. Well, the thing that you need to remember, and you already saw that in the previous presentation with the simulation, that the higher the frequency, the higher the tone. So that means, oh, there we go, the higher the pitch. Well, less waves in 1 second, so a low frequency means a lower pitch. Okay, well, there's of course a relationship between the cycle time and the frequency, and we can combine that in a formula. Well, the formulas look like this, and the formulas are actually pretty easy. It's just the opposite of each other. So the frequency measured in Hertz is 1 divided by the cycle time in seconds. So F equals 1 divided by capital T. Well, the opposite is of course the frequency. The cycle time. So the cycle time is 1 divided by the frequency. Make sure that you use standard units over here, and you will get an outcome in Hertz. So always use standard units in this case. Well, if we're talking about frequency and you look around you, then not everything around you can actually hear the same frequencies. well, as human, we have just a really small range that we can actually produce, and you see that on the left, and we have a frequency range that we can actually receive, that we can pick up. Well, if you look over here, you see that, over here you see that the humans are over here. A human voice can only produce, starting from 20 hertz, 20 waves per second, that's a really low pitch, and it can produce up to 5,000 hertz. And that should be a great singer like Adele or something. She can produce really high tones, and that means a high pitch. Well, you see that the range for different animals is of course different. If you take a look over here at bats, bats produce a sound starting at 10,000 hertz, and it ends up at approximately 150,000 hertz. So that is a huge range, and that is a range that is, well, we can't produce that as a human. Well, over here you see what we can actually hear. Well, we can't pick up any sound, all the sounds, but we can just pick up a tiny bit. You see, humans are over here, and humans can hear a sound that starts at 20 hertz. Well, that's really helpful, because we can also produce a sound that starts with 20 hertz, so we can hear each other. Well, and it ends up over here at 20,000 hertz. So that means 20,000 waves per second, and we can still pick that up as a human. That's a really high tone. But if you go beyond 20,000 hertz, we're not able to hear it. If you go in front of 20 hertz, we're not able to hear it. So you see over here, bats, they can hear sounds up to 150,000 hertz again. And that's the same as they could produce. So right now, there are probably all sounds around you, the same as with light. There are types of light that you can't see. There are also types of sound that you can't hear right now, but they are actually present. So in class, we will do an experiment about this, and we will see if your range is actually from 20 to up to 20,000 hertz. But that's a value that you need to remember also for the test. Okay, thank you for watching. Make sure that you do the homework for next lesson, and see you soon. Bye-bye.